Good evening. We're going to start Notes 15, Rational Exponents. Just a reminder that we do have a test tomorrow, and that test will be over Notes 11 through Notes 15, so these notes right here. Okay. So rational exponents. So some of the concepts we're going to look at is the definitions of a to the 1 over n power and a to the m over n power. Okay, so we're talking all about exponents and how we can take exponents and convert them to radicals. Okay. Remember, radicals is those square roots, cube roots, fourth roots, all the ones that we did on Thursday. We're going to talk about properties of rational exponents and then look at a couple application problems. Okay, so again, first concept is a to the 1 over n and a to the m over n. So first looking at a to the 1 over n. So it says let a be a real number and let n be an integer such that n is greater than 1. If we have the nth root of a, and if that is a real number, then we know that a to the 1 over n is equal to the nth root of a. All this is saying is, let's say n was 3. So this is saying like the cube root of a. Okay, well the cube root of a is the same as saying a to the 1/3 power. Okay, so whatever that root is going to become your exponent, the denominator of your exponent, when you change it from a radical to an exponent. Okay. So what would the 5th root of a become?
This would be
A to the 1/5 power. So it always just becomes the denominator of that exponent. So this one's pretty simple because we're only talking about roots and like our cube root or 4th root, 5th root, etc. The difference between this one and a to the m over n power is we now have something being raised to the m power. So it says let a be a real number and let m and n be positive integers such that m and n share no common factors and n is greater than 1. So it says if the nth root of a is a real number, then we can say a to the m over n is the same as saying a to the 1 over n to the m power, or in other words, the nth root of a to the m power. So using real numbers, right, it makes more sense when we have that. Let's say this is a to the 2/3. Okay. This is saying we can rewrite this as a to the 1/3 squared. So the denominator stays the same because that's our nth root. So this is going to be a cubic root. And the numerator becomes the exponent. And then we know that this is the same as the cube root of a and then squared. I would say this is the most common way you see it. But if you look at the next example, you can actually raise a to the exponent before you take the nth root. So for example, if we have the same thing, if we have a to the 2/3, okay, this is saying we can take a squared and then raise it to the 1/3 power. So the only difference is they swapped them. Okay. They're still both exponents. Okay, but for the first one, the one I wrote in red, we're doing the cube root, then we're squaring. The one I wrote in green, we're squaring, then doing the nth root. And since we're talking about exponents, the order doesn't matter, almost like in multiplication. Okay. So this is the same as saying the cube root of a squared. Okay, both of these mean the same thing. Both of these answers are two ways to say the same thing. Okay, so we're going to practice all of that in the examples below. So notice the first couple examples, they all have 1 in the numerator, which means we don't have any exponent that we're going to raise the whole thing to a certain number. We're only dealing with the nth root. And since this negative 8 is in parentheses, this tells us that we're going to put that negative 8 inside of our radical. Okay? So inside the radical. If it didn't have parentheses, then only the 8 would be inside the radical. The negative would be on the outside. Okay, so for example, this is the same thing as saying the cube root of negative 8. Okay, that 1/3 turned to cube root, and the negative 8 went on the inside. Okay, and then remember, now we're going back to Thursday's notes. Okay, so remember, if our nth term is odd, that means we can or cannot have a negative. We can. So look, 3 is odd, which means that negative 8 is okay. So we need to take the cube root of that negative 8, and you can do that by either thinking, okay, what number, if I cube it, gives me negative 8, or you do the prime factor tree. It is negative 2. So I'm going to show the prime factor tree in case you're not too sure. So 2 goes, and we're just going to focus on just the 8. 2 goes into 8 4 times. 2 goes into 4 2 times. This is the cube root, so I'm going to circle 3's. Okay, so notice I have 3 2's that I circled, which tells me I can take out one of those 2's to the outside. And since this is negative, this becomes negative 2 as our answer. Okay, so this right here is our answer. So we took it from the exponent, converted it to the radical, and then since we were able to, we simplified it to an answer. You're not going to always be able to simplify. Yes?
I have a question. As far as the test for tomorrow, I think a lot of our calculators aren't able to put the nth root.
Mm-hmm.
At least mine can.
Nobody should.
Nobody should.
Nobody should. You should have the basic.
There should no need to use the calculator?
No, you shouldn't need to use it.
You should just prime factor tree?
I would always do factor tree. Mm-hmm. And the only reason you would need it is, let's say this was a larger number here, and you need to use it to divide.
Okay.
Mm-hmm. So that'd be, yeah, you won't need to use your calculator for the nth root.
This is the most we'll have to do. Just the factor tree.
Yes, but not this simple factor tree, right?
Of course.
A little bit more complicated. But yes, you'll have the factor tree. But then remember, you have your notes, and in the notes, I gave you those little cheat sheets of like the perfect cubes and the perfect fours, so you can also use that. Okay, so let's look at the next one. Okay, so we have 81 to the 1/4 power, so how would I write that as a radical? So the 4th root of 81. Whatever's on that denominator is our n value for our root. Okay, and then here we can just do the same thing. We'll do the prime factor tree. However, we know 2 can't go into 81, okay, because 81 isn't even. So then we should check 3. Can 3 go into 81? So this is where you would need your calculator, right? If you couldn't do 81 divided by 3. I want to say it's 27. It is? Okay. And then 3 goes into 27 9 times, and 3 goes into 9 3 times. And since it's the 4th root, I need to make sure that I have how many 3's to circle? 4. Which I do right here. Which means I take one of those 3's out, and so the answer here is just 3. Yes.
Why do you break like the little box? Or why do you break the top and bottom part?
This part right here?
No. Okay.
Like right here?
Yeah.
That's just my answer. I won't box it if that makes it confusing. I'll just highlight it.
Okay.
Okay.
Sorry.
Wait, why did we take out 130?
Why did I what?
Why did we take out 1 3 out of the 4? Because there's 3 and 4. I mean, there's 4 things.
Oh, because every time I have a pair, in this case it's 4 within one group that I circled, I always take out one of them, always. So like for example, let's say this was 2 instead. Then I would have a group of 2 here and a group of 2 here, which means I would take out a 3 from this group and then a 3 from this group and multiply.
So then your answer is 9.
Yes. Yes.
Question, the last question, why was it negative 2?
Because it had a negative inside of the radical.
So
Mhm.
you picked up 1 2 and made a negative.
Yes.
Wait, so if it was outside of the radical, you wouldn't have the negative sign?
You would still add it to the answer. Yep. Yep. So the question is where did this negative come from? And we know it's negative because this is odd, right? And not only is it odd, we had a negative inside. So that's how I knew this was negative. If the negative was on the outside, so if this was just 8 and then the negative was out here, I would do all the work to write my answer and then I would just move the negative to the front.
It has no be negative either for the answer.
Yes, either way. Unless you end up with a negative, then you do negative times negative and get a positive. Okay.
That's from Thursday's notes.
That is, yes, that's from Thursday's notes. Like, for example, this one, right? So what is going under the radical here? The negative 100 or just the 100? Just the 100, right? The only way the negative comes with it is if it's like this. The parentheses tell us the negative comes with us. Okay, without any parentheses, it's only attached to the 100, which is good because this turns into the square root of 100. Okay, because if we have 1/2, that means square root, and we don't have to write a 2 here. Okay, you can, I won't mark it wrong, but it's just best habit that for square root, you just don't write that 2. Okay, and so then we can solve this. What is the square root of 100? 10. But since I had that negative in the very front, I have to bring it over. So my answer is negative 10. Okay.
So how come we didn't do the sign? Like, how we did that?
We could. Would you like to?
No.
We can. It's just
We can use the calculator.
you can use the calculator because everyone has the square root, just not other in roots. Or you just, I knew that the square root of 100 was 10, so that's why I wrote it. But yes, you can use the prime factor tree every single time. Okay, so then going back to this example, notice it's the same example, but now we have parentheses. So that means what is going to go inside the radical? The negative 100. So this is going to be the square root of negative 100. But remember, in order for a negative to be on the inside, the nth root has to be odd. Is this nth root odd?
No.
No. So then what's the answer? No solution. Okay, something a little different now. Now we have a negative attached to the exponent. So when we have a negative attached to the exponent, this means the exponent and the base, this thing right here is called the base that's attached to it, was moved from the denominator. Okay, so what we have to do is move it back to the denominator. So what that looks like, instead of having 16 to the negative 1/2 power, this is now 1 over 16 to the positive 1/2 power. Okay, so we had to move it out of the numerator because technically this is over 1. We moved it out of the numerator into the denominator, and what that did was get rid of the negative exponent. Okay, and what you'll learn eventually is that we don't like negative exponents. Okay, so anytime you encounter a negative exponent, they're always going to have you get rid of it by either moving it to the denominator or the numerator. Wherever it is, it moves the opposite. Okay, then we solve this. Oops. Okay, so we know that the 1/2 power is what type of radical? What is it called though? The square root. So we have the square root of 16. Okay, and what's the square root of 16? 4. So our answer is 1/4.
So then what happens to the 1/2?
From which step? Like from the very first step? Second step? So this 1/2 got changed into the square root.
You just put it into fraction form in that step, right?
Yes. So remember in the beginning of the notes, we had a to the 1/3, and we said that's the same as the cube root of a. Well, a to the 1/2 is just the square root of a.
Okay. So that's the original.
Yeah. We're just going from exponent to radical.
I feel like I would actually put the 2 at the square root. Would that be considered wrong?
If you did it in this course, no, because we're learning in this course. But let's say the next course, you're expected to already know that that's the same thing, so you may get marked wrong then. So I would try not to make it a habit. So if it's square root, just pretend, okay, it's an invisible 2. Okay.
We would have the same next week. But like for now, like just.
Yes, it would. If you did that, and I would mark it correct. Like it wouldn't be wrong.
Yeah, it's basically.
Okay. Okay, so now we have an example that no longer is just 1 over a number, which means we are going to have to transform this into a radical and then make use of the exponent. So I'm going to label these here. This right here is our exponent. This one right here is our radical. Okay. So when I convert this to a radical, this is going to be the cube root of 8 squared. And these are where the numbers went. This is the cube root. This is the squared. Okay, so if you think of it that way, you know, and if you write this out, and you know you have to put something here and something here. Denominator goes here, numerator goes here, always. Okay.
So
And
it's not that the 1 doesn't mean anything, it's just that it's 1. So you can't like square 1 by 1.
correct. So if I was to go back to like, sure, this one here, technically what I'm doing is I'm raising it to the first power. But anything to the first power is itself. So that's why we don't write it. It's almost like that invisible 2 for the square root. So, go ahead.
No, go ahead.
Okay, I was just going to continue. So to simplify this, we always do inside the parentheses first. So we're only going to do the cube root of 8. And we did this previously in a different example. So what is the cube root of 8? 2. Okay, so then this is going to be equal to 2 squared. Right? Because all I simplified was this part. The cube root of 8 became 2. I still had to square whatever my answer was. So then means my final answer, 2 squared, is going to be 4. So for ones that have m over n, which means it doesn't just have 1 over a number, we're going to have that extra step. Yes? Oh, sorry. Yes, yes. Okay. Okay. Okay, so same concept. Even though we have a fraction here, that entire fraction, since it's in the parentheses, is going to go inside the radical. So looking at this, which one is our radical? The bottom, right? And so this is our radical. And the 2 tells us we're going to write what? The square root. So this is going to be equal to the square root of 1 over 25 to the power of 3. Okay, so we simplify inside the parentheses first. And then remember, by the properties of square root, since we have a fraction, we can technically take the square root of the numerator and the denominator separately. So this is equal to the square root of 1 over the square root of 25 cubed. Okay, so I gave the square root to both the numerator and the denominator. Okay, then I can simplify. What's the square root of 1? 1. What's the square root of 25? 5. Okay, then I have to cube everything. Well, just like I could give the square root to both the top and bottom, I can also give that exponent to both the top and bottom. So this is the same as saying 1 cubed over 5 cubed. Okay, what's 1 cubed? 1, remember it's 1 times 1 times 1. And what is 5 cubed?
75.
Is it 75? I don't think so. 5 times 5 is 25. 25 times 5, 125. So that is our answer. So when we have fractions, we have to make sure we are giving the radical and the exponent to both the numerator and the denominator. Okay. Okay, what would be my first step here? Get Good, we get rid of that negative exponent. We need to make it positive. Since it's in the numerator, technically, right, because that's over 1, we're going to move it to the denominator. So it's going to be 1 over 4 to the 3/2 power. Always get rid of the negative exponent first. Okay. Then we convert it to a radical. So what number there represents the radical? 2. And that means we're going to do what type of root? A square root. So this is going to be 1 over the square root of 4 to what power? 3rd power. Well, what's the square root of 4? 2. So we have 1 over 2 to the 3rd power. And what is 2 cubed? 2 times 2 times 2? Not 16, not 12, 8. So it's 1 over 8. So remember, it's 2 times 2, which is 4. 4 times 2 is 8. Okay, so on your calculator, you should just be able to do 2 times 2 times 2. And then we have this one. So since the negative is inside the parentheses, is it going to go inside the radical or outside?
Inside.
Inside. And then which one of these determines our radical?
The radical, if the radical is even, then it would be restricted, meaning it can't be negative.
Correct. It's no good. It's no solution. The reason why it's no solution is because this 4 represents our radical. So this is saying the 4th root. Well, since the 4 is even, we can't have a negative. So if it's even, we can't have negative. Okay? So because of that, yep, that means it's no solution. Again, so since 4 is even, we cannot carry that negative inside the radical with us. Okay, any questions so far? Okay, so the next concept is converting between rational exponents and radical notation. So up here was us practicing what it means to have a number to a fraction exponent. And for these, since we were only dealing with numbers, we could get a numerical answer or we get no solution. But for these examples, notice a lot of the examples have variables in them. So we're not going to be able to simplify to a numerical answer. We're just going to convert it to what it would look like as a radical. Okay, so we have a to the 3/5. Okay. Oh my gosh, there. Okay, remember the numerator is our numerator. It's our exponent. The denominator is our radical. So, what root would this be? The 5th root of a to what power? To the 3rd power. Okay, remember, whatever is on the denominator is our root. So the 5's on the denominator, so this is 5th root. Sorry?
Do we solve that?
No, we can't solve this.
So it stays like that.
Yes, that's just our answer.
Yeah, because we can't square it. Right?
Well, yeah, we don't know what a is, so we can't do the prime factor tree on a to simplify the 5th root, and like we don't know what it is. So it just stays. Okay. Remember before when we were doing these examples, these were numbers, and we were able to simplify, but now they're just variables. So what that means, now that we could do a variable and we can do the numbers, we're going to mix them together into one problem. Yes?
In the last example, the radical was 5. So we're looking at a, we have to be a negative a.
Not that it has to be a negative a, but it can be a negative a.
Is it because there's no number?
It is because it's restricted. So all this is saying here is we can have a negative inside of the radical because this is odd. It's not saying it must be negative. It says we can allow that to be negative. Meaning if this was negative a, that's correct. We could still leave it that way. Or if it's positive a, we could leave it that way. Versus an even in value, we're never allowed to have negative. Okay, so when we start mixing numbers with variables, we are going to put each of them inside of a radical separately. Okay, so we're going to first do 5 to the 1/3 power. How would I write 5 to the 1/3?
Three,
3 to the 3 was 5.
5.
Good. So the 3rd root, right, of 5. So the 3rd root of 5. Remember, this thing that you've known as the square root your whole life, this is called a radical, and we just say roots. 3rd root, 4th root, 5th root, whatever number. Okay? How would I write x to the 2/3 power? the third root of x squared.
Do you always need to put that as parentheses when it comes to like?
The exponent, yes. Always need those parentheses. Because this is saying that that entire thing is being squared. Okay. So now that we have two roots here, do you notice that they are both third roots? Okay, they're both cube roots. If our roots are the same, we are able to combine the numbers or variables that are under those roots. Okay, so this means we have the third root of 5x squared. Okay, because if you remember the rule from the very beginning, we could rewrite this as the third root of x squared. Okay, where we put the exponent under the radical, it's the same as putting parentheses around the whole thing and putting the square at the top. So if we convert this to the cube root of x squared, and since they're both cube roots, we can just bring the 5 and the x squared and put it under one roof. Okay, so that's how we got the cube root of 5x squared. Yes?
Could you explain that again? How do they combine?
So the only reason they were able to combine is that they're both cube roots.
Oh,
Okay, so both of these have a 3. If one of them was different, we could not combine them.
And it's like 4 and 4 they combine.
Correct. These have to be the same number.
You said the exponent that goes with the actual number would then follow it under the value?
Correct. Correct.
Let's say instead of x, there was 2. Let's say, for an example.
Sorry, say that one more time.
Let's say, for an example, like instead of x, there's 2.
Oh, like this was just the number 2?
Yes.
So what we're doing here when we're putting the 5 and the x squared together, we're multiplying. So what you would do is you would do 5 times 2, and you'd get 10. And you would put the cube root of 10. Well, let me rephrase that because of that 2. This would be the cube root of 5 times 2 squared.
So if they were both variables, would it just be, what would happen?
If they were both variables, let's say this is y, then it's the cube root of yx squared. If it was x, it would be the cube root of x times x squared, which is the cube root of x cubed. Okay, we're going to go through all those different cases. Okay. Okay, so this is where the parentheses start to become important. They were important before with that negative, but now notice when we have this 1/4 exponent, is this attached to the y or is it attached to the 3y?
The big one.
Only to the y, right? Because there's no parentheses. So this is only attached to the y, which means the 3 is just going to come along for the ride. We're going to simplify the y to the 1/4 and then just put a 3 in front of it. Okay, so we know that 3 to the 1/4 is the same as doing what root? The 4th root of y. And the 3 that was in the front, we're just going to bring it to the front of our answer here, which means my answer is 3 times the 4th root of y. And again, that was because the 3y was not in parentheses.
The 3 is not next to the 4th integer, right? Into the integer. It's like 3.
Oh, yes. Yes, it's 3 times the 4th root of y.
So we don't use parentheses?
Like around the 4th root of y?
Yeah.
You could. If you did this, this would be correct as well. You technically don't need them because when you're writing this, and maybe I didn't do a great job of writing this, that 3 is much larger than that 4.
I see it now.
Yeah, right? So if you need to be that drastic on the test, be that drastic. Okay, or put it in parentheses. I'll understand what you're saying. Okay. So now let's look at this one. So first, what is the exponent attached to? The z, only the z. So we're going to first handle just this part.
Move it down to as a denominator.
Good, we're first going to move this down to the denominator, which means what stays on the numerator? The 9. So this is now 9 over z to the 3/4 power. The negative went away because we moved it to the denominator. Okay, 3/4 tells us that we're going to have what root?
The fourth root of z to
Good.
the I.
Good, so this is 9 over the 4th root of z to the 3rd power. Remember, you can put that exponent inside the radical, or you could have wrote this to the 3rd power this way. They're both the correct answer. And then we can't do anything with the 9 because we're not able to simplify that 4th root of z cubed because this isn't a number. If this was a number we could simplify, potentially we would be able to simplify the entire thing into some sort of fraction. But when we have variables in there, we cannot simplify further.
You said we could put them inside the brackets, right?
Yes.
Sorry, we could put the cube multiplied by 3.
Like this?
Yes.
Yes.
That's-
Yep, you could do that. That's the exact same.
And that's the answer.
That's the answer. Yes.
So because it was a negative, we made it a fraction. But we have a number instead of an imaginary 1.
Correct. Correct.
We have 9 instead of an imaginary 1.
Yeah, because that's technically like that. The only thing we had to move was the z, which means the 9 stayed on top. Mhm. Okay. Any other questions so far? Okay. Okay, so now we're going to do the opposite. Okay, so we did exponent to radical. Now we're going to do radical to exponent. Okay, the only thing you need to remember is that this root is always your denominator. This is the denominator. This is the numerator. Okay. Which means this is going to be b to what exponent?
3 over 4.
3 over 4. That's our answer. Okay. Okay, notice 7 and a are under the radical, which means both 7 and a are going to get an exponent. Okay, but notice we don't see anything here, and we don't see anything here. So if we don't see anything above the radical sign, we know that number is above the radical sign, 2, because that's the square root. And then inside as an exponent, if we don't see no number, we know that number is 1. So technically, this is going to be equal to
7A.
okay, so 7a, but then we have to do something with the 7a. Yes, parentheses, then to the power of 1 over 2. So again, why did 7a have to be in parentheses? Because they're both under that radical. Okay, so if you were to write,
It would just be A.
if you wrote 7a to the 1/2 on your test, that would be wrong. Because this is the same as saying 7 square roots of a, which is not the same as saying the square root of 7a. Okay, so if you have parentheses, that means everything that's in the parentheses applies to that exponent. If you don't, it's whatever it's attached to that exponent. So like this one. What's the only thing under the radical? A. So that means we're only dealing with this first. The 7 is just going to follow into our answer when we're done. So again, we don't see a number here, so we assume that number is 2. And we don't see an exponent here, so we assume that number is 1. So this is the same. If we're just talking about A, this is the same as saying A to the 1/2 power. But then the 7 comes along for the ride, and we put the 7 in the front.
So the A had a square on it, would it equal 27 A squared?
If this was a 2 as well, then this would be A to the power of 2 over 2, which simplifies to 1. Because remember, if the exponent matches our nth root, they cancel. Okay, because we talked about on the last notes. So like, for example, the cube root of A cubed cancel because they're the same number. The 4th root of A to the 4th cancel because they're the same number. Okay.
That was on Thursday's notes, right?
I believe so, yes. Mhm. Okay, what would this one be?
X 8 over 5.
X 8 over 5. The nth root is always our denominator. Okay, and that was it for that section. So any questions on concept 2?
I'm a little confused on the second to last question. Why didn't we have a parentheses in that one? Because it's a 7A compared to,
Oh, for this one compared to the other one?
yeah, compared to the next one after that one.
So that's because 7A is under the radical together. So they have to be in parentheses. But versus this one, the only one under the radical was A. Okay, so that means it's not 7A to the 1/2 power, it's only A to the 1/2 power. You could think of it even like this if you wanted to. But we don't have to put the parentheses there. Okay. Okay, so another little cheat sheet for you. So this is about the properties of rational exponents. So what that means is, what do we do if they're multiplying? What do we do if they're dividing, etc.? These are all the rules. So going through each one, if we are multiplying the same base, and remember, base is that number that is below the exponent. So in this case, our base is A. If the bases are the same, we add the exponents. Okay, so they give this example over here. We have x to the 1/3 and x to the 4/3. Both the x's are the same, so we add 1/3 plus 4/3 and get x to the 5/3. Okay, so multiplying, we add the exponents. Dividing, we're going to do the opposite and subtract the exponents. So if we're dividing with the same base, so like a to the m divided by a to the n, we subtract them. This is a to the m minus n. And here they use the example, x to the 3/5 divided by x to the 1/5 is equal to x to the 3/5 minus 1/5, which is 2/5. So multiplying we add, dividing we subtract, and then we have the power rule. The power rule states that if we have an exponent raised to another exponent, okay, so for example here, 2 to the 1/3 to the 1/2 power, we always multiply those exponents together. So we do 1/3 times 1/2, which is 1/6. So that's 2 to the 1/6. Power rule means we have a exponent and another exponent. Okay, let's see. And we kind of already did these next two right here. Power of a product, we just never gave them a name, and power of a quotient. So remember I said if we had something in parentheses that was raised to an exponent, we have to give the exponent to everything inside that parentheses. Oh my gosh, why is it not letting me write? Oh, I have something, okay. Oh yeah, this. Okay, so then this is 9 to the 1/2 power because we gave the 1/2 power to the 9. And then y to the 1/2 power because we gave that exponent to the y. So we already did that before. We just never gave it a name. And so it's simplified to 3y to the 1/2 power because 9 to the 1/2 power is the square root of 9, which is 3. Okay. Same with the one below. That's the power of the quotient. We still are going to give the exponent to both parts. But now everything inside the parentheses is just as a fraction. So we're going to give the exponent to the numerator and give the exponent to the denominator. This is very similar to when we take the radical or the square root. Okay, so what happens is they each got that exponent, and 4 to the 1/2 power is the square root of 4, and 25 to the 1/2 power is the square root of 25. So that's how they got 2/5 as their answer. Okay, so I would say the ones that I highlighted in green so far are new, right? We haven't talked about them in this course. Okay. The next one, we talked about it as well. Negative exponents. So remember we said if we have a negative exponent, we have to move that number to the denominator. Okay, and that's what they're doing here. They have 8 to the negative 1/3 power. Okay, then they move the 8 to the denominator, so 1/8 to the 1/3 power. The reason why they're putting it in parentheses and doing the 1/3 is because so you can practice this rule. Okay, but if you're writing it from here, this is the same as just saying 1/8 to the 1/3 power. Okay, so both would give you the same answer. Again, they are just writing it this way so you can practice that power of quotient rule. And then the last new one would be the 0 exponent. And all this states is that anything to the 0 power is 1. So any variable to the 0 power is 1. Any number to the 0 power is 1. Okay. So knowing these rules is going to help us do the next couple of examples. Okay? And again, you have this. This is your little cheat sheet because you're going to have this on the test. So if you can't remember what the rules are, you don't need to try to memorize them. Just make sure you have these notes. Okay. So let's look at the first example here. Okay. So before I solve this, I'm going to identify what property it is. Okay. So I have the same base. They're being multiplied. So what property is it? They are in common, but like based off of the cheat sheet we just did above. Yes, which is called multiplying like bases. So I'm just trying to make a connection to the example up to your cheat sheet up here. So this is the same as number 1, multiplying like bases.
And then we add.
And we add the exponents. So this means we add the exponents. Okay, so this is the same as saying y to the 2/5 plus 3/5. which is equal to y to the what? 5/5. And what's 5/5 if you reduce the fraction? 1, right? So this is y to the first power, which is just y. That's our answer. So if you get a fraction where your numerator and your denominator are the same, it always reduces to 1. That's the same as saying 5 divided by 5. Well, that's 1. Okay.
I have a question.
Yes.
Go up a little,
Go up.
below 0 exponent.
0. Yes.
I must not be paying attention. Why does something to 0 equal 1?
That is an excellent question. There is a proof for it, but for your guys' sake, I would just know it as a rule. I would just always remember anything to the 0 power equals 1.
Should we like highlight it or something? It's gonna be like needed.
I mean, you're going to need it for all future math classes, yeah? I mean, it's nice. It's something you should know.
Well, as of
Like,
tomorrow, we'll-
as of tomorrow, we'll go over that. I have the test with me.
Okay.
So I'll go over what you really need to know. I can't recall if this is on there, but this is something everyone should know, this. That's the same as saying everyone should know that a to the first power is a. Okay, it's just a rule. If you're going to be a math major, you'll learn all about the theory of mathematics to figure out why or who created this, but it's just a rule. Okay, next one. Which of those properties of exponents are we using? Dividing. So that's number 2, which is dividing like bases. And what do we do when we're dividing? Subtract exponents. Okay, so from here, I would just rewrite this because we have the same base a. Again, the 6 is not in parentheses with the a, so the 6a is not a base together. The 6 is just going to come along for the ride, right? It's just going to be attached to the beginning of our answer. So I'm going to bring the 6 down. I'm going to do a, and then I'm going to do negative 1/2 minus 3/2. So I'm subtracting them, so that's negative 1 minus 3, which is negative 4 over 2, which simplifies to negative 2. So this is 6a to the negative 2 power, but we don't like negative exponents. So what's going to happen? It's going to be a fraction. What's going to come down to the denominator, the 6, the a, or the 6a?
Oh, no, they just said A.
Just the a. And where's the 6 going to go? Stay on top. So this is 6 over a squared. That's my answer. 6 over a squared. When would the 6 come down with the a? If this was surrounded in parentheses. Good. If this had parentheses around it, then they would both come down together. However, if it had parentheses around it, would they be the same bases to begin with? No. One would be 6a and the other would be a, so you wouldn't be able to simplify it in the first place. Okay. So this looks like there's several rules here, but there's only one rule that we're going to use, or we're going to be able to use, and what rule is that going to be?
Negative exponents.
You were right, the power of quotients. It's a little bit of, actually, let me rephrase that. It's 2 rules, right? It's power of quotient, so that's number 5. Power of quotients because we have a fraction in there. And then we're also going to use what rule?
Power of product.
No, okay, fine. There's 3 rules. Okay.
The power rule.
The power rule, that's the one I was thinking of, but you guys are right. No, we can use all of these. Power of products, that's number 4, and then the power rule, number 3. We're using all 3 of those. Okay, power of quotient because we have a fraction. Power of product because the numerator is multiplying s and t. And power rule because the power rule states we are going to do what with the exponents? Multiply. Multiply the exponents. So we would take this exponent of a 4 and we're going to give it to every single one of these exponents. Okay, so this is going to be s to the 1/2 times 4, t to the 1/3 times 4, and w to the 3/4 times 4. So this would simplify to what? What would be s? 4 over 2. Because this is the same as saying 4 over 1. So we do the numerators. 1 times 4 is 4, and then the denominators. 2 times 1 is 2. Okay, and what would t be? 4 over 3. Good, for the same reason.
Wait, could you explain that?
Yes, so this is like 1/2 times 4 over 1. So I'm doing 1 times 4 and I get 4. And then 2 times 1 and get 2. Okay, and then what would I have on the denominator? Yes, but we didn't simplify the rest, so we're going to write it all step by step. So this would be good. 12 over 4. Yep. Okay, then simplifying this, now we can go to each of those fractions that are exponents and see if they simplify further. So what is 4 over 2? 2, so this is s squared. Can t of 4/3 simplify?
No.
No, we can't reduce 4/3 in any way. We just leave it as t of 4/3. And then what about w of 12/4? Can that simplify? To w cubed. And this is my answer. I would be able to simplify this further if all my bases were the same. Let's say they were all t's. But since they're all different, I can't use any other properties. Okay, any questions on that concept? Okay.
I have a question.
Yes.
Okay, so S for, oh, 4 always goes bottom. Never mind.
Perfect. Glad we solved that. Okay. Next, last one. I know it's pretty long notes. Of course, applications. We always have a word problem or an application because not everyone wants to be a math major and focus on just the mathematics. All of you are going to take math and apply it in some aspect of your career. So that's why applications are important. So it says, suppose P dollars, and this is a business example. So for those of you who need to take business calculus or anything like that, suppose P dollars is invested in an account that earns interest annually. If after T years the investment grows to $8, then the annual rate of return R on the investment is given by R is equal to A over P to the 1 over T power minus 1. Find the annual rate of return on $5,000, which grew to $6,894.21 after T years. So they're giving us all the values. They just want us to plug them in. Okay, so the first part says find the annual rate of return. Okay, which means annual rate of return, it wants us to find R. Okay, so that means it must have gave us A, P, and T. Okay, so it says $5,000 investment. Okay, this is going to be P because it says P dollars invested. Okay, grew to the 6,000 something dollars. Okay, this must be, oh, wait. T years investment grows to $8. Yep, right here. Investment grows to $8. And then T years is 6 years. Okay, so then this is, again, this is P, this is A, and this is T. So I'm just going to plug everything in. So I have R is equal to A, so 6,894.21, divided by P, which is 5,000, to the 1 over 6 power minus 1. Okay, so what we're doing here is we're using those properties of exponents, specifically the power of the quotient, and to give that 1/6 power to everything inside those parentheses. But the easiest thing to do is just simplify this parenthesis first. So can someone do that on the calculator for me?
Divided by 6, right?
Don't do anything yet. Just do this.
No, to simplify it,
To simplify it,
you're asking for it to go to a lower number?
I want someone to tell me what 6,800 divided by 5,000 is. 1.37?
Yeah.
Okay, 1.37. So R is equal to 1.37 to the power of 1/6 minus 1. Okay. This is where I'm not sure. Can you do a fraction exponent on your calculator?
No.
The only thing would probably like 5. That's not.
No. Can I see your calculator? No, you can't. This is not on the test, obviously, right? You can't use your calculator.
Is it 0.605?
0.67. When you raise it to the 1/6 power? I have to check.
0.22833.
Sorry, say that one more time.
0.22833.
I don't think that's correct either. I don't think that's correct.
What are we supposed
Do
to
you
do?
need to round up with this one?
We're doing 1.37 to the 1/6 power. No. I think you almost had it. Are you using your phone calculator? Oh, you have that calculator. See, you have too fancy of a calculator for this class. This is what you should have got. You should got 1.053869319 when you raise it to the 1/6 power. But then we got to subtract 1, which means really we have R is equal to 0.054. Let's round it, right? That's a big number. Okay, so when we do that, it's trying to have us find the annual rate. So usually rate is in percentage. So I would have to convert this to a percentage by moving my decimal 2 places to the right. So really my rate is equal to about 5.4%. So again, it's an example of an application problem. You won't have this tested since your calculator can't do this. The most you would have is to maybe just set it up. Like, can you set it up properly? You're going to solve more of these type of problems in college algebra, I believe.
Wait, what happened to the negative one? Or the minus one?
I subtracted it from here,
Ah.
which just got rid of that 1 in the beginning.
0.054.
She rounded to.
How, I just rounded it. Instead of writing 0.053869319, I just rounded it here.
Yes, the 8.
Yeah.